Encryption doesn't translate to the ability to prove a message sender's identity. The two factors, authenticity and non-repudiation, are ensured by the use of hash functions in digital signatures. A hash function is a one-way function. You have to find a hash, a characteristic fixed-length trait of a variable-length message. Cryptographic hash functions should also guarantee the maximum possible randomness of the result. Minimize the risk that the hash result generated from two different inputs would be the same, and make a hash result from two very similar sets of data dissimilar as possible. This means that for any text, computing the hash should be easy, fast, efficient, and not complex, while mapping a text to a signature should be very hard to achieve. Different inputs should also be mapped to different hashes. The use of hash functions is connected with a serious threat. While the security of symmetric or asymmetric algorithms varies, you can be certain that the hash functions used today are not secure. What's the reason for this state? The first problem that pertains to hash functions is the birthday paradox and the attack that exploits it. What is this problem about? If you get together with a group of 23 people, what is the probability that two of the people have the same birthday? As it turns out, this probability is surprisingly high. It's over 50%. There are 365 days in a year, so 23 people would be enough for the probability of discovering that at least one pair in the group share the same birthday to be over 50%. If 7 more people meet up, the group will increase to 30. The probability of at least 2 people in the group having the same birthday increases to over 70%. Why is the probability so high? First, since there are 365 days in a year, the first collision, or match, will occur after, give or take, the 19th attempt. 19 is the square root of 365. In statistics, a first match will occur likely soon after the square root of all possibilities. In a group of 20, you can create n times n minus 1 divided by 2 to 190 pairs. For each of the pairs, the probability of having the same birthday is 1 to 365. Using the data to calculate the probability, computing 20 times 20 minus 1 divided by 2 times 1 divided by 365 gives us 380 to 730. Slightly over 50%. Why even mention this? From the birthday paradox, we know that the risk of collision, having the same hash function result for two different inputs, is quite high. It's certainly bigger than it would seem. How can you protect yourself against this problem? How is this shortcoming addressed? There's one viable solution used. Hash function results have to be lengthened. We started with 128-bit length. Now there are even hash function results that are 512 bits long. What hash functions are there? The first function is the MD family message digest. These hash functions were developed by Ron Rivest. MD2 was published in 1989, MD4 in 1990, MD5 in 1991. The functions return 128-bit long outputs. For several years now, it's been known that there are efficient attacks on all versions of the MD hash function. For this reason, the functions are not considered secure and are not recommended. MD5 is still widely used, though, for example, in internet applications. Another option is using the SHA family of hash functions. They were developed by the NSA. The hash that's returned is quite longer at 160 bits. The first of the SHA hash functions, SHA-0 and SHA-1, are not secure. Since their publication, they've been shown to be susceptible to attacks. The security of the former is 39 bits, while the security of the latter is 63 bits. There's also another variation of the hash function, SHA-2. SHA-2 creates hashes that are 256 or 512 bits in length. While some Chinese researchers have announced that they have successfully cracked SHA-2, there's no official proof to support this claim.